I'm Doug Kirkpatrick. I'm the CEO of Eridan Communications. I know many of you. If you have any questions, please don't hesitate to throw them in wherever they are. The talk today is going to go at two levels. It's going to go at one level relatively high to motivate why you're doing what you're trying to do. The other level is going down into the weeds as to what it is in the physics and the engineering of what you're building as to what the essential trade-offs are that you're working against. So the outline of what we're going to go through today is first, let's talk about the future of wireless communications, where we're going, what some of the challenges are, what some of the dead ends are that we've run into. Software radios promise, some realized, mostly unrealized. Making a software radio actually work the way that it was originally envisioned. Some in here can tell me when that started. Where we are now, some of the imminent changes that are on the immediate horizon, some of them validated earlier today, and what that means for the paths forward and how we will see the wireless environment that we work in change dramatically over the next 5 to 10 years. Whoops, excuse me. In the future, we live in a resource-constrained environment. And when you think about wireless, you want to understand that there are three fundamental constraints that you need to worry about. We have constraints in spectrum, we have constraints in bandwidth, and we have constraints in power. And you need to work within those. And if we're going to expand what we're doing for data for everybody, everything coming over those pieces of operation, we need to do a hell of a lot better than we're doing today. And within that, there are three key ways that we're going to do that. I'm going to talk about them very loosely. Something called dynamic spectrum access, which many of you may be aware of. Something called MIMO or massive MIMO, which I assume most of you are aware of. And something which we'll call a universal handset, which has been kind of a holy grail in this industry for about 3 or 4 decades. I'm going to just show this, and then I'm going to go on. And if you want me to come back to it in detail, I'm happy to do it. We are humble engineers, despite the name Miracle. We didn't name it. One of our customers, when we were describing what it was, she kept asking questions of, well, so you can't do this. No, we can do that. You can't do that. Well, of course we can do that. Why else would you want to have it? She finally dropped down and said, this is a miracle, and the name stuck. And we're a little bit embarrassed about that, but that's where it is. We'll come back to this in detail. The fundamental thing I want to point out to you is this is not a theoretical discussion. This exists in hardware. It will soon be in product, out in the field, and you will soon be experiencing its benefits. Excuse me? Do you have samples? Yes, we do. And we have already sold samples to customers in both defense and commercial applications. The technology is not an amplifier. When we did this for the first 3 years, 4 years we were doing this, we said it's a polar amplifier. And then everybody said, well, we just take an amplifier and put it in front of everything else. And we finally realized that we just need to stop calling it an amplifier. Because while it technically is kind of, sort of, maybe an amplifier, it immediately leads everybody into all of that training that we've all had for 50 years, that if it's an amplifier, then that definition means it's a linear amplifier, and that means I use it like this and it has the following kinds of properties. And it's not. So about a year ago, we had a formative interaction with a potential customer, which I'll explain a little bit later, and we just said, we've got to stop calling it an amplifier, because immediately that leads them down the wrong path, and we coined this name the Switch Mode Mixer Modulator, SM3. That is actually a much better definition. I'll show you a block diagram as to why it's actually not an amplifier. As a consequence, we are simultaneously bandwidth efficient, spectrum efficient, and power efficient. And one of those essential trades that you face with a linear amplifier goes away. You can have all three of these simultaneously in a single device. We're going to talk about what we mean by those, because common knowledge today conflates bandwidth efficiency with spectrum efficiency. And they're not the same thing. Let's be careful about that. Bandwidth efficiency says I have a bag that is 5 megahertz wide, and how much data can I stuff into my 5 megahertz bag? That's bandwidth efficiency. Spectrum efficiency is I have a chunk of spectrum that I may be able to bargain for. How effectively can I use that spectrum? We're going to get into that in just a moment. What I'm showing here is an external measurement of our technology by Keysight Laboratories. This is 16384 QAM, 14-bit, 14 bits per hertz to be particular. Okay? So mostly what you would experience on your cell phone today is about 16 QAM. If you're in a really clean cell zone and you have a really good receiver on your phone, you'll get 64 QAM. They're dreaming of giving you 256 QAM. The only reason we stopped at 16384 is that's all Keysight can measure. Our underlying capability is to go to 16 mega QAM. Okay? So the game is changing. Let's make sure we get that. Spectrum efficiency. This is the miracle module you saw earlier. Just it can instantaneously change frequency, modulation type, and power level on the fly. So if there is an open band, it can move there. If the rightful owner of that band comes up, it can leave and go to a different band. This is something that we have wanted to do for decades. Power efficiency. This is the experience that taught us we had to change the name. So I was interacting with a systems customer, a really smart systems customer, and these guys are really, really good. And he said, okay, I get it. You're 50% efficient generating the LTE downlink signal at half-watt output power. So that's a 3-watt peak. You're 50% efficient, so that means you pull 6 watts of DC. Any of you in here see the linear amplifier thinking embedded in that? And I had to turn to him and I had to say, no, 50% efficient. We're half-watt out. We take 1 watt of DC. He looked at me like he just was convinced that I probably should run for president of the United States because I was a very good salesman, or lying, take your pick. So that's impossible. That's 160% efficient. And I sat there and stared at him for a second and went, we have that existential problem, right? You're sitting there going, I'm trying to explain to him that this is not his grandfather's technology. And how do I do that when I've already led him to believe by calling it an amplifier that it is? So it's not an amplifier. It's absolutely not an amplifier. Miracle provides bandwidth, efficiency, spectrum efficiency, all in one. Okay? You don't have to make a trade. Oh, I want to actually say something here. If you had a linear amplifier and you went from 16 QAM to 256 QAM, you'd expect to be able to do that with the right EVM. You'd have to make an efficiency trade-off. So we take our miracle system, we walk from 16 QAM to 64 QAM to 256 QAM to 1024 QAM to 4096 QAM to 16384 QAM, and our efficiency is 50% flat for every single one. Okay? There is no trade. There are different trades, but not that trade. So let's go into what we always thought software radio was going to be. You have on one end, coming in, the RF to digital converter, your receiver. Now on the other hand, you have the digital to RF converter, your transmitter, and you do stuff in the middle. Okay? We don't do any of the stuff. We do the other pieces. The part on the left-hand side, the receiver, you're really working on itty-bitty little stuff and trying to pull it out. We've almost got that done. The analog to digital converters that we've been spending a lot of time on, the low noise amplifiers, all the rest of that piece of what we're doing, That we almost have today, from DC to light. We can do 100 megahertz, 200 megahertz, 500 megahertz digitizations on the fly. It sucks power. It's perhaps not as nice as we'd like it, but we can do it. On the right-hand side, doesn't work. Right? You have essential trade-offs between bandwidth efficiency, tunability, and power efficiency. Why? We always wanted, this is right, one of those diagrams from one of those essential papers. You may have been the one to do this. Flexible RF hardware. Okay? Only problem is the transmitters aren't. If you take out a linear PA and you look out, and we've categorized a whole bunch of them, you have an essential set of trades. And the trade is, I can make it efficient, but narrow band. I can make it wideband, but not have efficiency. That's what Miracle does, by direct comparison. Okay? It's not a linear amplifier. We're going to get into the physics of this in a moment. So for those of you that are bored at this point in time, it will get fun. How do we do it? Two fundamental enablers. Gallium nitride, which really, for our purposes, didn't come into existence until about 2010, 2012 at the frequency ranges of interest for what we need to do. Okay? And the switch mode mixer modulator, which followed a direct polar architecture, which had been tried before in the 90s in silicon, and kind of limped to a partial success with a whole lot of lessons learned about where the hard problems were going to be. You get out of the switch mode mixer modulator incredibly precise signal control, as you saw with 16384 QAM. It's not linear. You don't need linear. You need precision, not linearity. Let's get that word out of our lexicon. This is the Wolfspeed V5 process. It's going to be released soon.
6 to 9 months.
So hopefully this year. We've been working with it with Wolfspeed for the last 4 years. So we have the benefit of having an incredibly close relationship with the foundry. I will dodge some questions about exactly what we're doing with the foundry if you ask them, because some of it is proprietary to us and co-proprietary to them, so I can't obviously reveal their stuff. But this is a 140 nanometer GaN HEMT process. It's GaN on silicon carbide. We're going to go into what makes this stuff work. The real critical part here is when you're doing a switch, your FT of the technology that you're working in needs to be at least 10 times the frequency of where you're going to operate the switch, because it's a square wave. And if you can't resolve the square wave with something like the 9th harmonic being present in the square wave, it's not a switch. It's that easy. No magic. If you want to have a decade of bandwidth, i.e. tune from 300 megahertz to 3 gigahertz, from 450 megahertz to 4.5 gigahertz, you can't have a matching network. We don't. You need to be 50 ohm matched at the device. If you're going to be 50 ohm matched at the device, and you're going to put out 3 watts, it's real easy to do the math. Okay? You don't need to go to MIT or Stanford to be able to do that math. Right? V squared by 2R equals 3. R is 50. Figure it out. Right? It's not hard. Okay? So bottom line is, if your output impedance is too low, you need to reduce the load impedance. You get more output power, but then when you do the transformation to come back out, you get squeezed, and you're done. Silicon will never do this. Okay? Gallium arsenide,
You get squeezed because of the bandwidth restriction of the matching network?
Yep. It's just math. Okay? It's what you've got there. All right, linear amplifier physics. You know, it's one of those things, and our CTO is a guy named Earl McCune, and I'm sorry he can't be here because his mustache alone is legendary. But the bottom line here is that everybody tells you all the wonders of linear amplifiers when you're an early engineer or physicist, and you never actually sit down and realize that linear amplifiers are designed to be inefficient. Because the principal operating point for a linear amplifier is in the peak of the IV curve, where dissipated power is maximum. So if you are absolutely the most linear you can be, you are by definition the most inefficient you can be. So when you think through that process and you actually think through what your trades are and you squeeze these complex signals into that space, you have just a couple of essential trades that you're faced with if you're going to use a linear amplifier. You have a couple of choices. This is the choice if you have an iPhone 8 or an iPhone 10 or you have some of the other devices. You have this in your phone for one or two of the bands that your phone operates on. That's a good idea. However, you'll notice that the peak operating point is still the most inefficient operating point of the transistor. So it's a compromise. It's not kissing your sister. This is good science, right? But you're still working from a linear amplifier. If you're going to do a switch mode mixer modulator, you're dealing with the same physics of a transistor, but you have a different circuit architecture, fundamentally different circuit architecture. We call that a direct polar architecture. That polar designation will be obvious in a moment. There is no free lunch. You give away 3 big challenges for the linear amplifier, and you take on about 8 for the switch mode mixer modulator. But if you need to go through, thinking about the Himalayas, if you need to go through 3 class 6 rapids or 8 class 2 rapids, I think I'll pick the 8 class 2 very much. Okay? If you're going to reduce power dissipation, this is your essential trade-off. If you're going to run Class A, you're running in this middle point. Class AB, you're still not getting a free lunch. If you want to switch, you're going between these 2 points. And it's just the math. You sit down, you look at where your dissipated power is, you look at how fast you can switch, and you work it out. No magic. This is what switching looks like. How fast you can switch determines your dissipated power in the switching time and your harmonic content and whether you can be clean. Transition times have to be fast. There is a premium on having a low on resistance and small amounts of capacitance so that the amount of charge that you need to move back and forth in the device is small. I promise the physics. So please, for those of you that now are not having fun, we'll go back to the other stuff. So when you do a switch mode mixer modulator, what you end up with is an operating curve that looks like this on the upper left, and you have outputs, waves, and dissipated power curves like you see in the lower right. And you can simply sit down and do a trade-off in what your frequency content is versus your switching time, versus your R-on, versus your capacitance, and figure out whether running a switch mode mixer modulator is good or bad, depending on what you're trying to do and what process node technology you have access to. It's not rocket science. Rocket science is hard. This is easy.
What is VK?
The knee voltage. This is what the flow diagram looks like. And this is why it's called direct polar. You bring in I and Q, which on our wonderful little chart look like Cartesian coordinates. You convert them to rho and theta, polar coordinates. You take the phase, you mix it with the frequency, and you end up with a phase modulator driver going into your final switch. And what that looks like is a train of square waves at the saturation voltage for the gate that is at the carrier frequency, phase modulated with the phase modulation, okay? What you get with the amplitude is you come up here and you just amplify that, and then you mix them together in the final stage. Now, that sounds easy, right? Nothing up my left, nothing up my right. Okay, truth in advertising. Remember I said 8 class 2 rapids, okay? The list is a little bit longer than for the linear amplifier, right? But there's a path. You really have to have very consistent resistances across your switches. It has to be remarkably consistent, because when you're building that square wave for the phase modulator, if it's not consistent, then you're going to have RC slew between your switching, and they'll gradually get out of phase with each other. Life sucks if that happens, okay? So that's step 1. Step 2, 0 is a problem. I mean, I think we all did the math in school, and somebody said, tell me what the polar coordinates are of 0, and then tell me how you get a clean defined in and out of 0 in polar coordinates. That's a problem. Bandwidth of going to 0 is a problem, because I think we all understand that there's a kind of a infinite pole there if you go to 0 and you flip around, right? Maintaining the efficiency across that decade tuning bandwidth means that everything that you have in your system needs to look like 50 ohms at all frequencies. So you got to pay attention. Don't let anybody move your cheese. Fast power slewing for modern signal types. The peak to average power ratio on the 4G signals is such that when you're looking at output powers and you're going down and coming back up again, we're putting more and more and more information content in there. And you've got to be able to really move in terms of being able to move that around. Harmonic power management. You're coming out with a square wave, guys. What are you doing with everything else? Now, if you do it really, really, really well, you get 88% of your signal to keep, because that's the fundamental content in what you've got out there. The efficiency numbers I showed you previously, that's not the switched power. That's the power in the fundamental. Okay? And then finally, one of the things that is a happy thing, so I'm kind of lying to you that this is one of the ones that's hard, you get a huge benefit in load pull for this type of signal. It is what we would refer to as stiff. You can't pull it, and I'll explain why. Switch resistance consistency. You need R-on versus VGS uniformity, or they won't switch. You get a sense as to how many switches we use. Each one of these layers is 4 switches. All right? And they're staggered in series to be able to build up that square wave to hit this final stage. Now, this meant we had to go out to look at all the foundries in the world and figure out if any of them were good enough for us to be able to use them. And I'm going to point out just one manufacturer labeled with a T, and we sampled a bunch of their devices, and you can see various devices here and what the scatter in those devices look like. And then this red curve is 100 iterations of the device from Wolfspeed that we use. And they lay on top of each other. The spread is sub% with the fit. Different foundries emphasize different characteristics. So you can't take what we do at one place and pick it up and put it someplace else, because those foundries, those GaN foundries, don't control for what Wolfspeed controls, okay? Getting to 0 output magnitude. Now we're all going to recognize that we're not mathematicians. I won't tell the joke about a mathematician, an engineer, and a physicist going to a hotel room, right? A fire breaking out. You guys have heard this, right? Okay, good. So I don't need 0. 0 is a philosophical debate you can have with a mathematician. Small enough is 0. And for everything that we have in any of our constellations, 80 dB down from the main signal is 0. Where we were stuck last time was 30 dB when they tried to do this in the 90s. Gallium nitride and a little bit of magic on our side, a little bit of Quentin, a little bit of me, and boom, we have 80 dB. And I think we say that, yes, we have a path to 130 dB. So 24 bits, not a problem until you get on the receiver side. So how do we do that? We cheat, okay? We do things that engineers do. You solve problems. What we do is we recognize that the RF driver in this switch mode topology is itself a switch mode amplifier of a sense. And all you have to do is work that side. And you can do all of these things in series. Technically, it's called product mode. So what we are doing is what every device designer and circuit designer for 50 or 60 years has endeavored never to do. For 50 years, everybody said we want to be in the linear domain of the transistor, unless you're making power switches, in which case you come up into the compressed mode. What we do is we start in the compressed mode and we go into product mode, where the output is actually the product of the voltages that are being applied on the gate and the drain, which everybody says don't do, and that's exactly what we do, right? How do you play this game? It's actually not that hard. We've done, as you'll see down here in the bottom, we've already done 50 megahertz up to 4 gigahertz in a single device. You play details as to what things look like. So we're doing this at 4 gigahertz. You have to worry about the 9th harmonic, which is at 36 gigahertz. On a gallium nitride device with the gallium nitride dielectric constant in the active region, most important thing to get everybody to realize is that ground is not ground. Okay? Ground is a local convenience. You cannot put node 0 in your design code and effectively believe that you have ground. Doesn't work that way. So when you end up looking at our final mimics, a lot of people have looked at them and said, this looks lopsided. I guess if you're looking with Cartesian eyes, it is. You have to think about what the electron sees. That's not the same. So how does power scale? Understand everything down here is the driver. That's your phase modulator. Okay? That's the power stage. This is a 3-watt device. Driver is about 10 times larger than the power stage, the power mixer. So you can go to 10 times higher power, and you're only going to use twice the amount of GaN. Okay? It does not scale linearly. And some proofs. You can do any waveform. It's a software-defined radio, for God's sakes. Digits come in. Any waveform you want goes out. We finally got a hold of the 5G NR waveform. We got a hold of it on a Wednesday. We plugged it in on Thursday, and out comes the 5G NR waveform. 2-spec, perfect. It's a software-defined radio. But it's doing it at power. There isn't a linear amplifier on the other end. So everything we as engineers wanted a software-defined radio to do, this does. There have been some classic issues with unipolar amplifiers. And drain lag, sometimes referred to as backgating, is one of them. This is a classic measurement out of NI, done, I think, in 2012. You take this type of drive signal, you put it into a HEMT, and what you find are two types of effects. You see these short spikes at the beginning, and you see a gradual recovery in the amplitude of the square wave over time. What that's coming from is the fact that the carriers are not being swept completely out of the active region. And so I have a dynamic impedance for the different frequencies. And as a consequence, I can't get nice clean signals as I'm slamming all over the place for these complex modulations. That's the switch mode mixer modulator that Eridan has developed. Now, I'm going to be truthful. We have not eliminated drain lag. The dragon has not been slain, okay? We've just arranged that the dragon take up residence someplace else, not where we want to operate. So we've negotiated with the dragon a little bit and moved it into a neighborhood that we're not interested in. And as a consequence, there is a very simple method to produce any complex signal. There is no feedback distortion required, right? Otherwise, why do this?
What are you showing on the right graph?
I take the same signal here. So what you've got is you've got this drive signal coming in the gold, and you've got the output coming out in the blue. And I'm showing you that there is no long-term delay, and I'm showing you that there is no spike on the leading edge of the square waves.
So this is the output of your phase modulator on the yellow?
This is the output of the, this is the digitally synthesized what should be coming out of the amplifier. This is the MATLAB of the IQ going in. And this is the output from the SM3 at power at 3 watts coming out. Okay? I'm not showing you any intermediate stages.
That's 3-watt output?
At peak, up here. Okay?
And that's for 3 watts driver and your 50% modulator?
Do the math, yes. We'll go into the details. Part of this is looking at your very fast frequency synthesizer and being able to move really quickly. The SM3 moves as fast as whatever frequency coming into it moves. Okay? So we can do end-to-end in about 10 microseconds and within an octave in less than 2 microseconds. So that's almost a megahop per second. The real detail here is if you're going to be using an unused band, a white space band, and you need to get the hell out of Dodge because the rightful user of that band popped up, you can be out before they ever even know you're there. Right?
How did you know he was there?
Your receiver's got to be looking.
So you listen and then transmit?
Cognitive radios, so now you're going to get into a space called CR, Cognitive Radios Dynamic Spectrum Access. There are, I want to be careful not to step on other people's property with respect to cognitive radio algorithms, et cetera. So you would typically be looking at a 100 to 200 megahertz band and say, I'm going to work here, and I have these 3 other stations that I have pre-populated ready to go to. And so what I'm going to do is I'm going to look here and know that somebody's not coming in, and I'm going to look here, here, and here, so that if I have to move, I already know where I'm going.
Can you tell that he's come in after you start?
Easily.
Okay.
Okay?
I'd like to know how you do that. If he starts transmitting, it's hard to... And you're transmitting. How do you know that he's on the band?
If you're staying in that band and you're TDD, your receiver is going to see something coming in that's not your modulation.
I didn't know it was TDD.
Most of these out-of-band single bands, if you're FDD, you need a hell of a lot more band space. And if you're sliding into a 7 megahertz television band, you don't have room to be FDD. It's silly to be FDD if you're doing that. Okay? You need to get rid of those harmonics. Everybody wants to have a flat filter, but you don't need a flat filter, okay? You know you're building the filter. You know where the ripples of the filter are. You move the filter around where you're going. Your insertion loss on that filter can be tiny, okay? Something less than 0.3 dB. Immune to load pull. I've done a bunch of radar work in my career, phased array work, or if you want to think about it, massive MIMO work. When the guys found this, they're like, yeah, okay, fine. And I was like, no, 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 you don't understand how, this is huge. Sorry for that. We don't need isolators. Because you're a switch, the back EMF from the backward propagating wave coming, transmitter number 1, transmitter number 2, output, output. Well, that output can reverse couple through that horn, and that electric field coming backward incident on this transistor is an electric field which creates a voltage which will slew a linear amplifier, okay? We're not a linear amplifier. We give a crap. We're either on, in which case we're a quarter of an ohm, or we're off. As a consequence, what you get out of that is an effective 22 to 32 dB of isolation from that backward propagating wave, which is all you ever get out of an isolator. Except isolators are frequency narrow. Now you have the ability to make a true phased array massive MIMO system, which is frequency agile. Can't do that until you do this. The other big thing is that because you're a switch, you don't amplify noise out of band. Think about that. Big problem with a linear amplifier is it amplifies everything. Well, I mean, you want that. If you don't amplify everything, you get criticized. But then realize you do amplify everything. Switch, you don't. You amplify what only is coming in at your signal. So the interesting thing here is you amplify phase noise. So you want to be really thoughtful about what your frequency synthesizer looks like. You do not amplify amplitude noise, right? Fundamentally different characteristic in terms of how you think about how you build communication signals going forward. Okay? Measurement. Just how good are you at that? Our phase noise coming in from our carrier has about 70 megahertz plus minus of bandwidth. So we go outside of that. We do a spot check. We're about 3 dB above KT. Okay? We look at that measurement and kind of go, it's low. We don't believe that it's 3 dB. We don't believe our measurement accuracy at 3 dB. All we know is it's a hell of a lot lower than anything else that's ever been done. Other benefits of the switch mode mixer modulator. You get inherent stabilities. You cannot oscillate. Not a possibility. You're a switch. You're in GaN, so you're thermally stable. We have inadvertently tested that. I'm not outing anybody, am I? I think I'm okay with that.
We tested it. Parts didn't blow up.
Never mind the founder that now works from Croatia to escape my wrath. But it worked great. Manufacturing stability. You have a huge R-on to 50 ohms delta. So if there's a little bit variation in R-on, you don't care. We've built almost 1,000 of these devices at this point in time, and we have 100% yield. Okay? Long-term operating stability, it's GaN. It's a rock. It doesn't care. It's a switch. It doesn't care. Now, implications. Yeah.
I just knocked out by 100% yield.
Yes, so are we.
That's after sort. So after mechanical sort on the, like a Wolfspeed side, when they'll do a visual inspection of their parts, So if they see that there's like a metal flake or something like that in the process, like it's a 3.5 process, but after they sort at that level, which was probably maybe a 2 or 3% loss, maybe. After that, every part we've ever tried has behaved identical. And in fact, we use the same correction tables across all our die. So we do a linear correction tables to get to like 16.384, you have a feed-forward linear correction. They're all identical. You haven't had to change that.
Thank you.
Sometimes what you thought were going to be class 2 rapids turns out to be calm water. You know, luck is always better than skill. Dynamic spectrum access. What do we mean by this, and what is it going to emphasize? It's not going to emphasize the bandwidth efficiency. You're not really trying to pump more data into the same channel. What you're trying to do is move to where they're not and use spectrum more efficiently. Why is that a challenge? This is what we're all used to, right? We've seen this map. I don't care how many incarnations of this map we've seen. It's a lie, okay? That's perception. Why is that perception? People did a measurement of New York and Chicago in 2012. This is the actual occupancy. And this is an overstatement of the occupancy, because if a band was touched by its rightful occupant in a 10-minute slice, it was dictated as being occupied for the entirety of that 10 minutes. So Mark, you could have come in and made a 30-second transmission, and that entire 10 minutes is checked off as being owned. Okay? So you kind of look at that, and you lay that on top of the other one, and you look at it and you kind of go, damn, there's a lot of white space out there. Now, let's be honest. Some of that white space is out of bounds, okay? There's stuff that's in there that would be really, really unwise to step on. Things like aircraft localization indicators, or FAA broadcast, or police and fire, etc. Those are hard, square keep-out zones. But there's large chunks in there that are for the television station backlinks, or this is a really fun one that I'm still struggling to try to understand. I think I understand how we got here. The entire television space is blocked off. Now, the reason we do that is because we have Channel 3 in San Francisco, and we have something else in San Jose, and we have something else in Sacramento, and they can't step on each other. But if you could use the empty channels in San Francisco or the empty channels in San Jose and just move around and be clean enough with your noise out of band that you don't step on people that you're not supposed to step on, all of a sudden, something on the order of 300 or 400 megahertz comes into play. And at an approximate value of $1 billion a megahertz for license, there's a lot of reason to go use that, if you could. Technology today can't, because you'd have to be able to move depending on what the local television space looked like, and it's not affordable to do that because I'd have to cram your phone with about another 6 or 7 different amplifiers, which you would not take and you would not want to pay for. But if your amplifier does it anyways, excuse me, your switch mode mixer modulator does it anyways, okay? WTF, right? Let's go get it done. Now, to drive this home, we all drove here. Some of you may have been fortunate enough to walk here. Some of you might have biked here. But sooner or later, we're going to get in a car and drive. And when you get out on that highway, unless you're really unfortunate, you are allowed to change lanes. Now, I want you to think about this model of what we do here, where in channel B, we've got 10 users, maybe dividing up 100 megabits per second. In channel C, they only have 5 users. Channel A, they didn't do good marketing, they have no users. But they have a 100 megabit per second channel. It's just sitting there empty. And the way we operate today is like getting on the highway, and you have a license to drive only in the first lane. You get a license to drive in the second lane, and you're not allowed to change lanes. Wouldn't it be awesome if we could take the high traffic channel, move it over to the low traffic channel, and give everybody the maximum access that they could have at that moment in time, right? You'd love to be able to do that. That's what dynamic spectrum access is, okay? We can't do that with the hardware we have today. You can now. Can't do that with Narrowband inefficient PAs, Miracle does that. I've already walked you through that. Massive MIMO. This is going to be beneath you. Sorry, but I had to start someplace. If you take a standard antenna, and I got Annabelle, Grandma, and Charlie, and I'm sending out my signal to Grandma, everything goes out radially. The same freaking signal goes to every one of them, occupying the bandwidth. And if my signal to Grandma takes up all the bandwidth, Annabelle and Charlie get squat. Okay? Obviously, we don't do that. We simply slow down how much Grandma can have. Massive MIMO is essentially a phased array. That's how I think of massive MIMO. And what it allows you to do is beamforming. It's simple. And Annabelle, Grandma, and Charlie each get their full 5 megahertz. It's that simple. We can do this. Now, there's a problem, however. First, that envelope tracking scenario can't do that in a phased array. They have some problems controlling the phase from an envelope tracked amplifier in order to be able to get the precision phase control to be able to beam steer what you need to be able to do. So you can't do that. You can not do the envelope tracking, but then you're going to be 6% efficient instead of 25% efficient, and the heat problem I'm about to show you gets a hell of a lot worse. This is a Doherty amplifier. 25% is generous. I think the world record for this particular type of technology right now is about 22%. But let's be forward thinking. Let's give them credit for 10, 20% more. You put a heat sink around all 4 sides. That's not what they do, but let's get a measure of how hard this problem is. And what you're going to find is those elements in the center, generally you can let them get to about 85 C and they'll still work. If you didn't have a really good cooling solution, they're getting to 235 C. So you have a 150 degrees C thermal challenge. That's the way I want you to think about this. Now, we've already demonstrated that we can do 40% at least under these conditions. Depending on what they're trying to do, we may be able to be at about 50 to 60%. But let's take 40. We're at 135 C with no heat sinking. That's not the right measure. The measure is 50 degrees C above 85. 150 above 85, 50 above 85. I think we all understand 150 is not 3 times as hard. It's a hell of a lot harder than that. So this is opening that door, and you're getting that efficiency with something that can do all of those complex signals to do all of that beam steering at once. Maximizing the data rate. Okay. There is a false conception that bandwidth equals data. It's even gotten into our words. How much bandwidth do you have? I don't know, 100 megabits per second. That's not freaking bandwidth, guys. Okay? Bandwidth is measured in hertz. That's data rate. And there's a false perception that carrier aggregation solves this problem. Carrier aggregation doesn't solve this problem. It makes it worse. I take a wider bandwidth signal. Okay, I just use more frequency. And then I pair it with another piece of signal someplace, and I just made that harder because now I've got to actually take more edges off to deconvolve that and get my data out. If I actually look at the net efficiency of that process, it goes down. This is what we've already done, right? That's the signal I showed you at the beginning. You just go right by the process of what you're doing. If you want to do the comparison, 16384 QAM, the signal, what we've already done, 16 QAM, 64 QAM, 256 QAM. Yes, sir?
So the reason nobody does 16384 QAM or 16 million QAM, like you said before, has nothing to do with the amplifiers. It's that the Shannon's law makes it completely impractical to do that.
Incorrect. And I'll prove that to you in a moment. Okay? So if you go and do 24 bits, you can't even see the dots anymore. And 16384 QAM is where 16 used to be. There's your array that you want to worry about. Okay? Now you're right. If I want to do 24 bits in a mobile cellular system, I'm not going to do that. But if I want to do 24 bits in a point-to-multipoint system, where I have a static receiver and I have a static transmitter, and I'm about 800 meters away, and I generate the gain that I need between those two signals, and for 24 bits, I need about 63 dB of gain in my structure, 63 dB of signal-to-noise margin. I can easily do that, okay? Can easily
I
do.
trouble finding a receiver that will receive that.
I'm going to leave that off for the moment.
But you're going to come back to it.
Nope. There's pieces that I'm not in a position. We've got 10 patents that have issued. We're going to have to leave some of these things to the reader to figure out.
But you can tell us about the patents that have issued.
Correct, and the receiver has not issued. Okay? This is just for fun. Most of us, I see some of you that are going to look at this and go, who the hell are those people on the screen? Okay, for those of you that don't know, on the upper left is the Star Trek Enterprise. It was a TV show that played from about 1967 to 1970, crossed a bunch of racial barriers. I think we had the first biracial kiss on screen, bunch of that kind of stuff. Okay, I'm sorry, I'm off a little bit there. And they had this amazing communicator that everybody looked at and said, that's science fiction until we came out with these things, right? Everybody still is wondering how in the heck they stand up there in geo up in space and just come down and they can talk to all these people at the same time. You just look at the size of that main dish and you can pull out the numbers. It's about 525 meters across. And you can look at how many massive MIMO arrays you can put on that sucker. And of course, I mean, you do have a plasma reactor in there. So I mean, God's sakes, you don't worry for power. Do the link calculation, and you've got about 135 dB of margin. So you don't have any problem whatsoever. All right? Bottom line out of all of this is that the game has changed. The technology has changed. What you can and cannot do in terms of moving the links forward and getting that process out has changed. You'll see this in products within the next 3 to 5 years. I'm happy to take any more questions.
Question?
Yeah.
How do you get the amplitude to be so precise on the output of your switch, your mixer switch?
That isn't. If I did not make that clear, let me try.
The short answer is we use feedback.
No, we don't.
It's a feed-forward system.
It's a feed-forward system only.
But we represent it, and so you have a DAC, sends out data to an amplifier. That amplifier has feedback, because it's a narrowband system. The amplitude packet's a narrowband system. So it's very, on an op-amp, you can get 50, 60 dB of linearity, no problem.
Let's go through this for a moment.
And then on top of that, you put a buck, basically.
There's 2 or 3 pieces to your answer. All right? So let's be careful. The first is all of the nonlinearities in the system, and there are many. All right? There is amplitude nonlinearities. There are phase nonlinearities. And there are amplitude phase coupled nonlinearities. The beauty of the gallium nitride system is they are all, as Quentin pointed out earlier, measurable and incredibly reproducible. So the first thing is that when we get I and Q and we convert that to rho and theta, the first thing we do is we know these are the rho and theta that the customer, the dude on the left, has asked for. That then converts into, as he just indicated, a lookup table of these are then the values that we are sending out because we know these combinations of values lead to those values. All right? So that's the first thing. That is the feed-forward nature of this gets to that. Now, there is going to do layers within layers within layers. I apologize, but I'm trying to give you the actual correct answer. This is the other part of the answer, right? We're doing the physics thing, right? This is the first truth. I'm sorry, I lied to you as a freshman. Classical mechanics. Okay, now I'm going to tell you about relativity. Sorry, now you're a junior. I'm going to lie to you again and tell you about quantum. And oh, sorry, now I'm going to lie to you again in graduate school and tell you about relativistic quantum. Right? So I'm just trying to peel the layer back each time. So the first thing that you need to understand is its IQ goes to rho theta, goes to a feed-forward lookup table. All right. Now, in this diagram, we're showing you something called a LAM. All right? The LAM is the feedback piece that Quentin was talking about. It is, we are sending this signal in, we want this voltage to be applied to the drain of the SM3, and we need to apply that voltage exquisitely precise, okay? And so as that voltage comes in, the LAM is this green line, and it is on a feedback circuit locally. It's not looking at the RF output, it's looking at the voltage it's producing compared to the voltage it was commanded to produce. Okay? And that's where the feedback is. There is no feedback coming from the RF. Clear?
So what's the bandwidth of that feedback?
The bandwidth of that feedback right now is about 100 megahertz. Okay? And yes, there are things that you would want to do to increase that for very, very greedy things that you would like to be able to do down the road.
Local feedback or?
Yes.
It's very local.
Just think of it as a source follower and an op-amp. You're probing the source follower.
It's a little bit of a lie, but not much. Okay?
It's okay.
You know, sitting down and drawing circuit diagrams, just how much, you're right. I think, yes, sir.
Are you going to come back in a couple of years and tell us how the receiver works?
I'll do better than that. I'll send Earl. Okay? He with the mustache. Okay? Because he knows the receiver upside down, inside out, and backwards. The challenge you have on the receiver, so let's actually talk through that for a moment before I take your question. The challenge you have on the receiver right now is it makes no sense commercially to deliver 24 bits per hertz. You'd get no credit for it. You'd get no value for it. So commercially, what it makes sense to do today is to roll out 8 bits per hertz. Give everybody 8 bits per hertz compared to 4 bits per hertz that they have today. You double their bandwidth. I don't know about you, but if somebody...
Wait.
We don't talk bandwidth that way, remember?
Bits per hertz. You double their data rate. Excuse me. Thank you, Sensei. I'm sorry. They do it to me all the time, too. The word amplifier still comes out of my mouth, and they throw things at me. Okay? I'm old. It's hard to teach. Probably come out with 8 bits to start with. Get everybody up to 8 bits. The beauty of what we've done is that moving from 8 bits to 10 bits to 12 bits to 14 bits to 16 bits is mostly a firmware change and a receiver change. The receiver that will go in will have more capability than we will initially harvest. So there will be 8 to 10 years worth of lifetime in anything that we do just in firmware, and we can simply roll those out over time as local conditions ask for more data rate. Okay? Yeah, I'm sorry.
Well, to be honest, I got a whole bunch of questions, but
what's the comic line? I'm here all night.
So
You can go out to dinner with him.
okay. So GaN devices, I think it's been established that they're high efficiency and high voltage and high linearity for quite some time. And polar amplifiers have been around a long time. I built one in an RFIC 20 years ago.
First polar amplifier was built in 1917.
Yes. So you haven't really told us what specifically Eridan is doing that's different, other than to say sort of it's patented, right? Because GaN is being done by the transistor company.
I'm sorry. I thought I
existing.
I'm sorry. I thought I did that.
Well, we don't. I mean, it's
No.
well, what's in that circle with the X through it?
Hold on a second. Hold on a second. I'm going to go to one thing that we have done, which independent of your value, the patent office established its own category for it. Everybody has always lectured for 60 years to avoid what we're doing. Okay? There are many, many, many patents taught art to avoid product mode. And that is what we're doing. Okay? You can't do what we're doing if you don't do product mode. And if you don't do product mode, you won't get 80 dB, you won't get 130 dB, you won't do LTE, you won't do 5G, you won't do MIMO.
Okay. So, I don't believe there's any currently operating systems that require 80 dB of...
You don't need 80 dB because you're thinking of a linear amplifier. You need...
I understand that, but you're saying, I mean, you're talking about how you've got 80 and you're going to go to 130.
Ah, I'm sorry, you're missing why that's important. Why that's important is because as you go to more and more complex signals, you need better and better and more precise definition of where you are.
100% understood. The issue is that, just to use an example, if you have some system that is currently in operation and it takes X amount of power to get a certain number of bits per second per hertz, let's say it takes 100 milliwatts to get, and you're able to do QAM 256, right? Because you have a real channel with thermal noise. So it takes 100 milliwatts. If you're going to go to QAM 16384, the power is going to be in the kilowatts in order to do that, right? No matter how good your amplifier is, there's thermal noise that you're working against.
True. So I'm going to simply ask you that we take this offline because we have lots of data on systems where with thermal noise and white noise processing on the receive side, you can gain another 30, 40 dB. This is not speculation. This is being done. DARPA funded an entire program in that space. It's done, all right? We're talking about harvesting technologies that were demonstrated 10 years ago. So this is not speculation. I don't need to develop a new receiver topology. Everything I just gave to you is all done on the digital side. All right? It's not magic. All right? It exists. Now, does that get you to 24 bits? Probably not. Today, it probably gets you to between 16 and 18 bits. Done. Then you've got more work to do. What you've done, and what I'm trying to evangelize, for lack of a better description, is that linear amplifier has gone down this path. As far as we are concerned, we believe the linear amplifier is a dead end.
On the transmitter.
On the transmitter. Okay? It's a dead end, right? If you go down a different path, you can open up a different set of trades, which we have been able to demonstrate opens up a different trade-off envelope for a system optimization. If you're looking at this from the standpoint of a 5G system, we're doing 5G already in a way that linear amplifier guys cannot do today. It's that simple. And we're a tiny company with a tiny amount of funding compared to massive companies out there that have been trying to do linear amplifiers for 50 years. That's all you're saying.
Well, I'm not disagreeing that linear amplifiers are inefficient. You can do better. But I think
it's not just efficiency.
Okay. We'll take it offline.
Thank you. Sir.
What is the range of 5G going to be?
Range.
Yeah. How
distance, frequency, data rate.
Distance.
Oh, good Lord. What frequency?
What frequencies are we going to operate on?
That's a damn good question. Right now, if you're asked, that's a question for the FCC, not me. If you ask the bigs, they will tell you we're going to 28, we're going to 39, we're going to 60 gigahertz. The reason they are doing that is because they have two existential challenges with the way they're doing what they've got. The first is, given the linear amplifier technology they're using, they have a limited ability to drive the ACLR roll-off. Therefore, they need to find frequency allocations where they have the space not to step on their neighbors. And as a consequence, they're going up there. The minute, for those of us that have done microwaves, and I've done everything from Ka band up to 600 gigahertz, there are some problems as you go up in frequency, like drywall all of a sudden becomes a barrier to your energy, which is not a happy thing if you don't have a transmitter in the closet you walked into inadvertently. Range? I don't know. Because if 4 gigahertz, massive MIMO, 256 by 256, the design specs that I've seen coming from folks like Nokia, Ericsson, etc., they're targeting 3 kilometers. Okay? The design specs for point to multi-point links at higher data rates, they're targeting 800 meters. Well, it depends what you're trying to do. And the reason I'll make the latter point is where I live in the center of San Francisco, I have one choice of cable provider today. I want to get your heads off of mobile telephony, okay? I have one choice of cable provider, which happens to be a subsidiary of the evil Comcast, right? And I could pick anybody. I could say evil AT&T, I could say evil Charter, because I don't think anybody that has a cable provider is happy with them. And the reason you only get one, I'll appeal to my VC friend, is business. They come in, they put in the cable, and they get, I don't know, however many people they get, 70% of the neighborhood. Whoever is going to pay to put in a second cable, data has shown they get 30% of whatever the first guy did. So their ROI, by definition, is 3 times lower. So if you didn't put it in first, there is no business reason to put in a second cable. Ergo, there is no competition. Ergo, you're screwed. So the first thing that I figured out when we started seeing this is within 800 meters of my home, and I'm in the center of San Francisco, I'll grant you that. Within 800 meters of my home, there are 8 40 gigabit per second plus fiber data points, okay? And not from the big 4. Some from the big 4, some from others, okay? Now, the closest one to me, and I'll grant you that I probably would not select them as my internet provider, is PG&E, that has a 40 gigabit per second fiber link going into a substation, as I pointed out, right? Going into a substation that has 100 kilobits of usage. But they're mandated to have the fiber in there. So they have 39 plus gigabits of free bandwidth. That fiber is 127 meters from my house. Yes, I've measured it. So if I did my link with a massive, with a 256 by 256 massive MIMO antenna going to my home at 4 gigahertz, my absolute Shannon limited link to that position, something on the order of 18 to 20 bits per hertz.
What do you mean by 256 by 256?
256, it's an array, 16 by 16 array.
Okay, nice.
256 transmit, 256 receive. Now, sometimes they will advertise it as 256 by 512. They'll have 256 transmitters and 512 receivers with cross-polarization. Okay, so there's a lingo that massive MIMO is developing. Yes, sir. Did I answer your question?
Sort of. Yeah, sort of.
Try again.
Okay, how about, okay, so
I want to answer before I move on.
what, can they get spectrum at 4 gigahertz?
Oh, shit, yes. There's a butt ton of spectrum from about 3.7 up 3.7 to 4.3, 3.7 to 4.2. And particularly locally, this is the other thing that is kind of miraculous. If you can actually control your edges, and by that I mean your spectral crap that you leak out, and if you can control your beamforming, if you're a massive MIMO antenna, then there's tons of spectrum available to you, okay? And that is really, that's the game here, is going back to looking at that spectrum diagram and recognizing that if you can go where they aren't, so if you could be dynamic, which massive MIMO would not need to be, or if you can control your footprint, there's lots of room for you to work below 6 gigs.
What kind of bandwidth would you get at 4 gigahertz?
So there is a discussion going on. This is open and on the table. To my knowledge, there is a discussion going on with the FCC from 3.7 all the way up to 4.2, 500 megahertz of bandwidth.
Yeah.
Okay.
Okay, 500 megahertz per second. Okay.
That's a lot.
Yeah.
Okay, sir.
We had an EE380 speaker, I'm guessing maybe 20 years ago. And I might be-
I wasn't there, I'm sorry.
My recollection is after telling us a whole lot about wireless communications and new protocols and such, and
Yeah.
reducing antenna size and putting antennas on chips and radio between chips and so forth, he explained that the technology should work, but technically it was in violation of federal law to do what he was proposing. But he said that the license fees we expect to collect on these patents should easily cover the lobbying of the FCC to bend the laws. I've heard you say some things that sound a little like you said, if you're broadcasting on a channel and then the rightful owner comes along, you can back off.
Yeah.
So let me.
You said if you back off before he even knows you're there, you know, you
So
said
let me-
it's
let me-
technically legal.
No, what I'm actually advocating the FCC is doing. All right, so let me go through something called diceband, so you know what it's doing, and just make sure that you understand that what we're talking about is diceband on simply more than steroids. Okay. So the first experiment they've done, and this is actually laughable, just so you understand what I'm about to tell you. The first experiment they did in the AN SPY-1 radar band, which I believe is 1920 to 1960 megahertz. Now, what's really unique is that in the United States, the SPY-1 radar band is blocked out throughout the United States. Now, this is a radar that goes on ships. Okay? This is the Aegis radar, right? Now, we're a forward-thinking country, I think, sometimes. And we have Fargo, North Dakota with the Aegis SPY-1 keep out. So good. So why do we have that keep out? Well, the reason we have that keep out is because the Aegis cruisers use their radars to map where the shore is as they approach the coast. And so we the country, thought that it was a good experiment to do dynamic spectrum access to allocate 10 megahertz channels from 1920 to 1960 and have sensors along the coast to see if an Aegis was in range, in which case they would use a master controller to shut off those bands, and everybody who was in those bands would have to vacate those bands. There's an entire IEEE community dedicated to doing experiments in this space, and some of you may be involved in that. If you're not, I encourage you to, because they need wise minds. What's that?
Raytheon.
Not exactly.
Applied signal technology.
Good enough. The thing that they've done so far is they've done an experiment on the east coast of the United States for the last 2 years, where they have made those bands available, and they're doing, and the diceband protocol, which is going through the FCC for approval, has 3 types of users, right? It has primary licensed user. If the primary licensed user is in the space, nobody else is allowed in the space. If you're in the space, you must vacate the space in, get this folks, how fast do we think is reasonable to vacate that band? 90 seconds. Okay? They're setting a really high bar. Okay, 90 seconds. Okay, 90 seconds. Okay. Now, there is a secondary licensed user. Okay? A secondary licensed user can be in the band if the primary licensed user is not in the band, and they kick everybody else out. Okay? And then there is a third tier of user that is called a general access user, who pays the least fees. If the primary or secondary are not there, then the general access users may have access. Okay? This structure has been running. It's not thought, right? It's not concept. Yes, it took the FCC 13 years to get there. Okay? Because honestly, I will tell you, the technology didn't exist. And really, it wasn't even the radio technology. It was the management technology, be able to figure out you're in, you're out, you're in, you're out, and communicating all of that. General access users is a first come, first serve. Okay? In, out, in, out, in, out. And they actually do that across the bands. So if you get booted out of the 10 band, you move into the 20 band, move into the 30 band, move into the 40 band, and reverse. And they have the cognitive radio algorithms already. Let me rephrase. I said algorithms plural. They have an algorithm running. We won't debate whether it's a good algorithm or a bad algorithm, the best algorithm. That is way so far outside my expertise. I'm not going to even comment on it. But I will say it works.
Pays fees to whom?
You said the general pays the least fees. Whom does he pay fees to?
Everybody is paying fees to Uncle. You license band from Uncle. Okay? That's where how you license access today. Okay? And the fees that for a 2 seconds, the fees for a general access user are about a factor of 50 lower than the fees for a secondary user, that is about a factor of 10 lower than the fees for a primary user. That's what the experiment has shown so far in the bidding. Now, whether that holds, it's a factor of 500. That's not small, okay? So if that holds, as you move up, there's a whole dialogue of what the economics look like. Yes, finally, I'm sorry to make you keep waiting.
Your presentations are always wonderful. Fab, you spent some time on finding the right fab. Now you've got one, and you get success. How do you scale that up? How does that work? Is it difficult to reproduce fab and make millions and hundreds of millions of these things?
I'm trying to figure out how I can answer your question without outing things.
If you build it, it will come.
Oh, no. No. We are actively in discussions with 3 very large companies in 3 very different spaces that have asked that question for obvious reasons, right? I think every single one of those applications would say that 5 years down the road, they want to have access to at least 100 million units per quarter, okay? Obviously, depending on success, blah, 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 right? So one of the first things we have to show them is, how do you do 100 million units per quarter? And does that require, the amount of power that it, because the Wolfspeed foundry is in Research Triangle Park, North Carolina. And that's presumed to be the bottleneck, because the silicon ASIC is presumed not to be the bottleneck. That's a correct assumption. But Wolfspeed is already getting ready to build a 6-inch, actually is in the process of building a 6-inch line. And our requirements, these are tiny die, and they will get tinier still. The die that we're using are research die, and Quentin, who's our lead GaN designer, is profligate with making sure we have lots of places to test things, which is good because we make mistakes. It's good to measure. And as a consequence, go to production, that die size is going to go down to maybe 1.5 millimeters by a millimeter, maybe 1.5 millimeters by 1.5 millimeters. So we're using 6 square millimeters today. It goes down to 2 square millimeters. We will use about the 1/3 of the capacity of the 6-inch line for 100 million units per quarter. Okay, it's not that's not the challenge. Please God, let that be the challenge. I will be a very happy man. Okay. Yeah, and given what, so I understand that, and I understand the question on manufacturing yield and those pieces. We were concerned when we got started 4 years ago, that we'd start with like 10% yields, and if you had 10% yields and you had all of these problems, then why the hell you do this? And so we were focusing like hawks on what our early yields were going to be, and we grilled Quentin regularly what he'd done. Were they cherry picking the chips that were coming off of the Wolfspeed foundry, because everything worked, nothing broke, until we deliberately started breaking things, right? I mean, because we're engineers, we break things. That's what we do. And we were stunned at what our yields were. And that shifted our thinking, and quite honestly, it shifted the foundry's thinking too, in terms of what they could do to move their process to something that allowed them to have greater wafer yields. So simultaneously, what we've seen in 4 years is the price per square millimeter come down by almost a factor of 7, and our yield remain at 100%. Our costed yield, because the stuff that they don't ship us, they eat. Okay? So that's, I mean, on the GaN side, it's stunning. That's all, and that's one of the benefits you get with a switch compared to a linear amplifier, because you're not looking at transconductance. You're operating here and here, and it either is or it isn't. It's a 0-1 criteria. There's not bins of it's got this G sub M and that C or anything else. It's in or it's out. Anything else? Yes, sir.
On a little bit off-topic thing here. In recent years, there's been interest, and there was recently a documentary produced on Hedy Lamar's involvement in the development of frequency hopping and other radio security techniques. Are you at all familiar with the full story there? What is your reaction on these stories?
I'm not familiar with the story. I have, let's see, I know my bio was sent out, but I should, in full disclosure, tell you that I was formerly chief scientist and program manager at DARPA. And as a consequence of one of my programs, I deployed into the field with a Special Forces Aviation unit for 15 months. So I had extraordinarily personal familiarity with the 45 pounds of radio and 38 pounds of body armor that I got to wear at 127 degrees and 9,000 feet. So you take a very personal learning to two things. A, frequency hopping saves your freaking life. Second, if I could have all of those radios and something that looked like this, lots of big, hairy, strong men would want to kiss you, okay? Because it would make a big deal. Frequency hopping is a lifesaver. There's no other way to put it.
I think to add to that, I believe there's a program next week on PBS about her.
It's this Friday, 2 days from now at 9 o'clock.
Very good.
And frequency hopping, actually, I don't know when it started, but the first time we were dealing with it was in World War II.
Yeah, IEEE Spectrum had an article about her, I think it was 1989. It's easily looked up.
She is named as an inventor on a patent that covers that.
Article by Robert Schultz.
Sir.
Is there anything known more than just the newspaper story about the new Apple very high bandwidth personal radio system?
If I did know anything, I wouldn't be in a position to talk about it.
One of the reasons there are taboo slots in the television band is because of the poor selectivity of early receivers. Has that problem gone away?
Television receivers or radio receivers?
Television receivers in the television band.
So if you're using digital television, which everybody does today, the receiver technology changed.
I'll say
if you don't have enough selectivity in the DTV, you never get the DTV signal. So the selectivity changed by about 40 dB when you went to DTV.
Okay.
Out-of-band selectivity you're referring to.
Jason channel rejection.
Same, yes. We're using the same definition.
Okay.
Yeah.
Can I ask one more question about the drive system? We have feedback to determine precisely a level, and it sounds like you have a very low impedance voltage follower that is what actually drives out. Is that really what you've got in a sense?
The patent's in, so we can talk about it.
Yeah, that's you can think of it as a common source, a source follower on an op-amp. And on top of the source follower, you have a buck converter that sets the voltage level. So you have a small voltage difference above your voltage regulator. So you basically have a variable voltage regulator. And you have feedback from that source follower coming back on your op-amp. So you're always holding that right voltage on a circuit that's switching very, very quickly.
Right.
And the mixing point is the choke, right? On the other side of the choke, it's mixing. So because you know the voltage very precisely on the top of that choke, and you're regulating it with 60 dB or more of feedback-based gain, right? you can get very, very precise signals.
So this sounds suspiciously like an amplifier to me, even though you're calling it a switch.
Nope, nope, nope. That amplifier's up here.
So
That's what he's saying.
So on top of the lamp, so the lamp is an amplifier. Yeah, that is an amplifier.
Yeah.
Yeah, that's the amplitude modulator amplifier. That's just amplifying the amplitude signal.
Right.
But the actual supply for that source follower, the drain side of it,
Yeah.
is a buck converter that's basically like an envelope tracker. That's the right way to think about it. So there's about 1 volt of overhead in there. Okay? Now, that 1 volt of overhead and this switching point, it all gives you that really nice, elegant system that's really, really efficient. So if you're thinking about the drain efficiency, you take the drain efficiency, that source follower efficiency, and the buck converter, that stack up. That's basically the efficiencies Doug is talking about. That's the DC to RF conversion efficiency, and including the driver portion of the PA.
So yeah, that is an amplifier up top. And technically, the phase modulator is an amplifier too, right? So what you've chosen to do is you've chosen to take one linear amplifier, break it into 2 very different amplifiers, align them in time to picoseconds, and mix them. That's what you've done.
You literally mix the amplitude path and the phase path. And if they don't convolve just perfectly, it looks really, really ugly.
It's foobar. if you don't do it perfectly, it's foobar. It's just yes, sir.
What kind of minimum geometries do you need on your chip?
140 nanometer.
That's not so bad.
What you asked a question, and I'm going to give you that answer, and then I'm going to tell you the question you should have asked, and I'll give you that answer.
That's even better.
Okay?
Yeah.
So what we need to do what we're doing is 140 nanometers. We are evaluating additional approach. What would we really like? About 70 to 90 nanometers would be the ultimate place that we would like to be able to see this, because then as we look at it and we do all of the trades, that's what would push us up into the maximum capability for this technology in the 6 gigahertz and below band.
And do it efficient.
And do it with just painfully good efficiency. If we look at the 60 gigahertz band, that's a different technology node. That's probably not GaN. Okay? You go up there, you need to have a 600 gigahertz technology capability. There are other options to do that, and you'd be at a lower power point.
And up there, what kind of distance range do you get?
Hundreds of feet.
Hundreds of meters.
Hundreds of meters. Okay.
Okay, and it's self-securing because it's atmospherically absorbing.
Yeah.
Okay, so
Those
there.
through walls?
Some.
Some.
Like what,
That
any
strictly,
ratio?
that 60 gigahertz signal is strictly for point-to-multipoint broadcast and getting away from the cable guys. That's the only thing it's good for. If you're going to do that inside a house, go home.
Yeah.
Right? Somebody chooses to boil noodles in the kitchen, and the kitchen will be off limits because the water vapor will absorb all the signal that you put in. I mean, it's nuts. It's nuts. It's nuts. We were doing some tests earlier in my career on a Navy ship, and we were in Hawaii, and we'd made it work in Virginia Beach in November, and we went to Hawaii, and it didn't work. Gosh, what's different, right? I mean, it's just that much of a humidity change, and it went from we can almost get it to work to, yeah, it's not even getting off the deck of the ship. So, any other questions? Yes, ma'am, sir?
My question maybe is still good. You mentioned the phase is decided by the lookup table.
Phase is not decided by a lookup table. What you're doing is you're taking I and Q, and you're bringing it in, and you're converting that to what the rho and theta are, and then that goes into a lookup table of 8 parameters, 7 parameters.
No. There's 3. You're taking the phase table. You're talking.
No, we got the whole. I'm talking all the voltages and everything else that come out of rho and theta that we then send forward. There's about 6 or 7.
There's 3 tables.
There's 3 tables.
Yeah. Of 4,096 points in each table. 12-bit.
We're cross convolving your answer here. We have a half a dozen things that we control. Out of that, knowing what those controls need to be, we know what the answer needs to be. We know what the nonlinearities are. That's a lookup table. Okay?
And that is the gate voltage of the modulator.
There are remember what the driver looks like. There's 7 stages to the driver. Remember that we are playing games inside the driver to do product mode. So there are multiple signals that are coming out of that depending on what you're doing.
I think you're asking if you have a phase path, that as the phase changes, or the amplitude changes. So as the amplitude changes on that choke we were talking about earlier, and it gets really low, we go into this product mode, the phase will change the signal. So we have correction, linear direct lookup table that corrects the phase as you change the output power. I don't know if that's what you're asking about. Yeah.
Yep.
So, and it's, that too actually happens to hold very accurately across all the chips.
But what's the resolution about the phase paths? Like,
So we,
Do you want it in time or you want it in frequency?
I don't know.
so like, what level do we correct phase? We correct it to 0.2 degrees.
Would you tell me what you mean by product mode?
Sure. What we mean by product mode is the best way to show that to you.
Simple.
Hold.
The voltage of the pipe and gate and the drain. So normally you operate. It multiplies. So if you as you change the, if you can change the voltage on the drain or you change the voltage on the gate, those two actually come together. So part of that, now Doug maybe will explain.
Yeah, what you're doing, I meant 101, 201, 301, right? What you're doing here, I showed all of these voltages being the same. That's not what we do. I told you I was lying to you. So what we do is in product mode is we reduce this amplitude. We reduce the amplitude of the signal going into the gate, and that's the 201 lie. The 301 lie is that I showed you the driver that has multiple stages. We actually reduce the voltages at multiple stages in the driver in order to accomplish this without too much swing, for lack of a better description.
You can think about it if you think about the IV curves of a transistor.
Yeah.
Right? As you slide down the gate, you need to drive the gate less.
No, I understand what you're saying. So you're compensating for this interaction in
Absolutely.
the device itself.
Absolutely.
Now I understand.
Absolutely. That's what we're doing. And that's what product mode is, and that's how you get enough vertical resolution that when you do 16384 QAM and you're in near zero, you have 0.4% EVM, which is in that signal that I was showing you. We're at their measurement limit. Okay? And that's
Basically, a more complicated way of doing digital to analog conversion.
Actually, it's a nice
Overall,
it's almost a nice way to think about it, digital to RF conversion.
yeah, whatever. Analog is lower, higher frequency, whatever.
You're just accommodating the GM variation, essentially, in the transistor?
Actually, the right way to think about it is we're accommodating the AC coupling from the gate to the drain.
The Miller effect.
Yeah.
Oh, okay.
because otherwise the gate signal will go right through.
So what you end up having, like you were talking about the phase correction table, you get feed through, and so you end up as you drop the power on your choke. If you take a transistor and put it in an RF signal, you keep dropping the power. What you'll find is it'll come down, it'll come down, it'll come down, and then it'll start to come back up because the drive through the gate starts to become the dominant signal. It goes through a phase change, 2 phases cancel, and then the gate becomes a dominant phase and the power actually goes up.
This is a gate to drain to source, drain to gate capacitance effect?
Gate to drain, yes.
That's what I meant to say. Okay, thanks.
Yeah, that's why product mode is important.
Earl has it really well documented in his book.
Yeah, so our CTO unfortunately was at a customer running a test today, and and he'll come back to give the receiver talk in 2 years. I just threw him under the bus.
Yeah.
You'll kill me for that. But, hey.
But we'll kill you for 2 years.
Okay, that's fine. I'm fine with that. I'm fine with that. He'll kill me. He'll give me beer afterwards. It's okay. Yes, sir.
Are there any constraints on the input signal you give to this?
No. Constraints on the input signal. Let me see if I can answer your question with data.
The constraint is that it's I and Q.
I want to answer.
Some intelligence.
Well, I used to test some of these things because I have to be able to read them. And I could put in random signals for I and Q and make something work. Would
So-
would tell me I could maybe multiplex 100 input signals on this?
So I want to show you this because this is, there's actually a huge amount of value in here, and this is why we'll be talking to the FCC in a few weeks. These are all kinds of standard signals, right? Here's a 5 megahertz LTE downlink, here's a 5 megahertz LTE uplink, this is 16384 QAM in a WCDMA envelope. That's GMSK, there's your 1.4 megahertz LTE, everything exactly following what it's supposed to be doing. And we got, as I said, we got the 5G NR signal, we put it in, it worked. And I say this jokingly, but I'm serious. You got 6G, send it. You got 7G, send it. It's a software-defined radio.
We've literally taken a signal and split it into two signals and transmitted it out of the same system. Okay, so you can pretty much do just about anything you can think of. I mean, there's obviously you have to think about how you construct your signal for it to be reasonable in some sense. You have to take into account the bandwidth of how much bandwidth this thing can transmit and those kind of things. But as long as you stay within those kind of notionally reasonable constraints, which are far broader than anything like a 5G NR signal is, it'll work. It's actually really, people at Keysight, when we tested and did that 16384 QAM test over the air, it wasn't far, it's maybe like 1.5 meters, but it was over the air. It worked. They were like, this is incredible. So, I mean, yeah, they said they hadn't seen anything like it.
The critical piece that I want to draw your attention to is, if you look at the LTE signal, one of the challenges that we're dealing with today is these coattails down here, and everybody has them, and that's one of the artifices of the construction of the LTE signal. And you'll note that that's not in the 5G NR signal. This is one of the things that classic linear amplifiers are having a lot of trouble with, and we have zero trouble with it. And this is a huge potential value, not in places like San Francisco or San Jose, but in places like the southeastern United States and other places where you have secondary providers who are kind of limping along behind the big four in terms of where they can get spectrum. And they might only have 4 megahertz of spectrum, and because of the shoulders that they have the keep outs for the LTE, they actually only get to put a 2 megahertz signal in there. Well, with what we can do for them with these types of software created envelopes is they can now use 3.5 megahertz out of their 4 megahertz. Never mind putting any more bit depth into what they're doing, simply expand the shoulders out and you give them 80% more frequency. That's also a big deal. That comes into the spectrum efficiency side of the house of what we can enable. And we do it at 50% efficiency. So those are, when you start to think about the kinds of things that a truly software-defined radio at power that's nice and wonderfully clean will give you, that's a big deal. And those are kinds of things that we'll be in a position to realize relatively early. I mean, sure, we'd love to sign a contract with Verizon and start doing all kinds of things with Verizon, but Verizon's, you know, it's like signing a contract with Apple. When can we have 100 million units? It's not a discussion worth having right now, right? So crawl, walk, run. I hope that answered your question.
Yeah, I'm kind of curious if you've had any patents denied.
No. Well, so it's important to... No, has nothing to do with DARPA, has everything to do with Earl. Earl was, I only threaten my coworkers with extraction. It has a lot to do with our CTO, who was the CTO at Tropian, which was the company that tried to do this in the 90s. So we know where all the dead bodies are buried. So we know everything that we have to invent over. We know which patents have expired, and we know what IP we need to avoid. So that's the reason that we have an unblemished record at this point in time.